Good afternoon, everybody. Next, yes. Good afternoon. I'm Ron Esteban. I'm with CENIC Network Operations, and this is AmLight's Express and Protect network, supporting collaborative astronomy in the Americas and Africa. And without further ado.
Hello. Well, first I want to thank you, CENIC and organizer, for inviting us here to wonderful Monterey. My name is VASILKA CHERGAROVA. I'm from Florida International University, from Center for Internet Augmented Research and Assessment. And here is a short outline. I'm gonna present a summary of astronomy projects in South America and Africa. What is AmLight, network connectivity, and other activity with CENIC, and conclusion. So let's start with projects in South America. There are over 84 astronomical observatories in South America, and 65 of them are located in Chile due to the dry climate. Chile alone hosts about 55% of the world astronomical observation capacity. And here are a few examples for observatories that are in operations. The Magellan Telescope, Gemini, Very Large Telescope, VLT, the Atacama Cosmology Telescope, Atacama Large Millimeter Submillimeter Array, or ALMA, the Polar Bear Cosmology Large Angular Scale Surveyor, or CLASS, and there are many more. There are few that are in construction currently: the Simons Observatory, the Vera Rubin Observatory, the Giant Magellan Telescope, and the European Extremely Large Telescope, or ELT. Projected observatories include the Tokyo Atacama Observatory, or TAO, the Fred Young Submillimeter Telescope, FEIST, which was currently renamed, you may know him as a CCAT, and the Cherenkov Telescope Array South. Here are a few more details of the telescopes in northern Chile. On the top left, you can see Vera Rubin Observatory, for which I will provide a little bit more details later. Right under is ALMA Observatory. ALMA Observatory has about 66 radio telescope dishes in the Atacama Desert in northern Chile. Close in this area by ALMA is the Simons Observatory, which is located at altitude of 2,500 meters. There is also Gemini Observatory, which has two 8.1 meter telescopes. One is in Hawaii, Gemini North, and one is in Chile, Gemini South. Another project that I would like to mention, the Cosmic Microwave Background Project, which is the next generation ground-based experiment, which has 21 telescopes in South Pole and in Chile. So there are observatories that consist of 1, 2, or more telescopes, and there are radio telescopes that consist of one or multiple array of telescopes. And they compile data from multiple geographical locations, and also data is sent to multiple data archives around the world. For example, the Event Horizon Telescope included 8 telescopes at 6 locations in 2017, and then in 2018 there were 9 telescopes at 7 sites, and currently they're adding more and more locations. Let's look at the South Africa. The majority in astronomy research in Africa is located in South Africa, again due to the dry semi-desert climate that they have, that provide clear sky most of the time of the year. The South African Astronomical Observatory, or SAO, is the National Center for Optical and Infrared Astronomy in South Africa. SAO includes several telescopes such as the Birmingham Solar Auxiliator Network, the Kilodegree Extremely Little Telescope, or KELT. There are also a few telescopes that are part of Las Cumbres Observatory Global Telescope Network. There are a few that are part of Monitoring Network of Telescopes, or MONET. There are a few Solaris telescopes, Super WASP South, and the Southern African Large Telescope, or SOUT. Another radio telescope that I would like to mention that has been producing an amazing research in the last few years is MeerKAT. MeerKAT is an array of 64 dishes in the Karo region, and it's operational since 2018, and currently is operationally oversubscribed. Many datasets from MeerKAT are no longer proprietary and are available through an archive interface. MeerKAT is a precursor for SKA, the Square Kilometer Array. SKA will add 133 additional dishes to MeerKAT and 512 aperture array stations in Western Australia. The end of construction is envisioned for July 2029. What is interesting here is that SKA will archive over 300 petabytes of data per year. And the data will have to be transported, processed, stored, and distributed to its end user around the world. So to accomplish all this, to accommodate this all astronomical research and data transfer, the South American Astronomy Coordination Committee, or SAC, was created in 2011. SAC is comprised of representatives from various astronomy projects and network operators in South America, Africa, and the US. The goal of the SAC is to coordinate the network needs of astronomical projects to improve their resource planning and implementation of operational connections. In 2020, AmLight established a 100 gigabits per second link using the South Atlantic Cable System, or SACS, and the West African Cable System, WACS, to Cape Town, South Africa. And Africa was invited to the SAC in 2021. So what is actually AmLight? AmLight is an international research educational network built to enable collaboration among South America, Africa, and the US. And what is important here is to mention that National Science Foundation, the Office of Advanced Cyber Infrastructure, or OAC, and the International Research Educational Network Connection, or the R&C programs, has a long history of supporting the astronomy community. Next, AmLight is based on partnerships with research educational networks in the US, South America, Caribbean, and Africa. And it's built upon layers and layers of trust and openness by sharing infrastructure and human resources. And those logos are the partners of the collaborators. The AmLight vision is to continue enabling collaboration among researchers and network operators by providing reliable, sustainable, scalable, and high-performance network connectivity and services. And the focus for the next 5 years includes supporting SLA-driven science applications, improving network visibility and management, enabling integration between AmLight and network-aware science drivers, adding new network and cloud services, and minimizing the human role in network operations. And I will elaborate on this a little bit more. AmLight current network connectivity includes 600 gigabits per second of upstream capacity between US and South America and 100 gigabits per second to Africa. Planned for 2023 is the addition of 200 gigabits per second from Brazil to US. There are over 2 terabytes of international connectivity. So if you look at the map, the green one is AmLight Express. AmLight Protected is in white color, and plus the waves provided by Red Clara and Sunrent Tenet, they're in pink. Those are the partners. In 2022, Red Clara added additional 100 gigabits per second from Panama City to Fortaleza. There are 3 network access points in Florida, one in Boca Raton, one in Jacksonville, and one in Miami. 2 network access points in Brazil, in Sao Paulo and Fortaleza. Then one in Chile, one in Puerto Rico, one in Panama and South Africa. What we are trying to work on now is to expand AmLight to Atlanta, Georgia with 400 gigabits per second of total capacity, 300 of which will be from Boca to Atlanta and 100 from Jacksonville to Atlanta. And also to provide dedicated connections to ESNet and Fabric. Collaboration at its finest. So here we can see all collaborators and partners in the AmLight Protect and project and how they leverage their resources. Different color segments represent collaboration and links sharing to augment capacity for science and education. The goal here is to engineer resilience in the form of multiple paths to support end-to-end and the community they serve. The dashed lines are links in progress or planned for the future. Here we can see country-to-country connectivity. There is connectivity and aggregation from all points to South Florida. There are planned upgrades currently in motion, and we have planned some new installations. We have connectivity of 100, 600, 400, 300 gigabits per second, but all links are over 100 gigabits per second. As I mentioned before, here are more details about this amazing astronomy science instrument called Vera Rubin Observatory. Vera Rubin is a large aperture, wide-field, ground-based optical telescope under construction in Chile. First light for the engineering camera is expected in July 2023, while system first light is expected in February 2024, and full survey operations are aimed to begin in October 2024. Now those dates are estimated because of COVID. The dates get moved back and forward. The telescope will have the largest digital camera, 8.4 meters, which will take a picture of the southern sky every 27 seconds and produce 13 gigabytes data set. Each data set must be transferred to the US data facility at SLAC in Menlo Park, California, within 7 seconds inside this 27-second processing window. So the challenges for the research and educational networks, what they're facing is like high propagation delay in the end-to-end path. The round trip time, or the RTT, from the Summit station to the US data facility in SLAC is approximately over 180 milliseconds. And if there is the slightest loss of packet, if there is like a 0.001% packet loss, that will compromise the Vera Rubin Observatory application. So to address those challenges, multiple network operators involved in the long-haul network for Vera Rubin have an ongoing network engineering effort. The Network Engineering Task Force was officially created in 2017 to support that effort. The net is comprised of representatives from multiple organizations and research educational networks. So from US we have Aura, we have AmLight, Internet 2, ESNet, Slack. We have some representatives from Formulab and NCSA. From Latin America we have REUNA, the Chilean Research Educational Network. We have Red Clara, the regional, the two Brazilian networks, which is RMP and RedNet. And some of the data will be processed and stored in Europe. So we have AN2P3 from Lyon, France. We have Renater, the French Research Educational Network, GIANT and GISC from UK. So the goal is to coordinate the steps to interconnect all efforts toward a manageable, cost-effective, secure and scalable end-to-end network infrastructure. So at the AmLight site, we have set up a goal to increase automation by applying a closed-loop control to achieve this SLA-grade network resilience. Closed loop is a mechanism of self-management functions that can collect, analyze, decide, and act based on data. The table here shows the levels of automation and the corresponding descriptions. The fundamental goal is self-management comprised of self-properties. And this can reduce dependency on human administration or centralized management systems and enable adaptation to changing environment. In a way, the goal is to have less human interaction and more automation. And how we are achieving that? Here is more granular information on the instrumentation. On the express path, we have instrumented with in-band network telemetry and persona servers. At the AmLight management plan, what we try to do is processing telemetry reports, isolating and detecting traffic anomalies, validating performance thresholds, computing risk profiles of optical and IP layer metrics in a closed loop, and reacting to packet loss and packet performance in real time. The AmLight metric for success is to not miss the data transfer window for the data set produced from the telescope. So here we have the mechanism of closed loop network orchestration. The green boxes represent INT-enabled switch. In this case is a Tofino switch, Noviflow Tofino switch, which submit in-band network telemetry report to an optical packet telemetry collector, which produces a summary report. This is the blue line going up. The summary report is submitted to a learning system, in this case Behavior Anomaly and Performance Manager, represented in this graphic with the purple box. From there, the learning system has two options. One, to send it to a live person at the NOC center, or to send an intent to a SDN orchestrator. The orchestrator then will have to send the instruction back down to the switch to adjust its behavior. And the roadmap ahead is to traffic engineer the network starting with less than 5 seconds and gradually go to less than 500 milliseconds for year 5 of the project. So several measurements and monitoring tools are used at AmLight. Different use cases require different tools. What we use SNMP, SFlow, and Syslog. In addition, we have 2 telemetry solutions. We also use Zabbix monitoring tool. Additionally, AMPAT AmLight is part of Manners initiative to improve security and resilience. Manners means mutually agreed norms of routing security. It is a global initiative that helps reduce the most common routing threats. The benefits of all these tools for the research community is providing complete network visibility, providing historical data, capability to identify and resolve outages, identify security threats, monitor SLA, and also recognize points for improvement. Here are a few other projects that we are supporting. This is the Large Hadron Collider open network environment. We also support Open Science Grid, Partnership for Advanced Throughput Computing, or PAD. This is also a new project, the Event Horizon Telescope, and other ground-based telescopes in Chile and South Africa. Last but not least, I would like to mention the ongoing RNC SDX intercollaboration, or the software-defined exchanges intercollaboration, which was initiated in 2018 and is currently hosted by CENIC. It includes representatives from the three SDXs, the Atlantic Wave, the Pacific Wave, and Starlight. And the goal is to improve interoperability and share the progress and evolution of the SDX activities. In addition to this collaboration enabled projects involving the hosting of the Generation 4 node at AmPad-AmLight to support the PRP Nautilus project, and also the use of DTN as appliances within the exchange points, personal implementations, measurements dashboard, collaborating on different demonstration of different data movement tool sets, and providing supports for science drivers from various projects. In conclusion, AmLight has many links and multiple paths connecting its sites to support astronomy projects. For example, from Chile to Jacksonville, there is more than 25 possible paths that the packet can take. With the new architecture, we expect to properly load balance network services across the links while respecting users' constraints and requirements. AmLight will handle any SLA-driven packet loss intolerant and sub-minute response time expected science application, and the goal for AmLight is to be prepared to react to network condition under 1 second and to be able to anticipate issues and steer traffic out before an adverse event happens. And finally, with the closed-loop control implementation, the AmLight engineering team is able to focus on engineering a new service rather than manual activity. The goal is to have more software development and automation. Thank you. So if you have any questions?
Yes, we have plenty of time to, if you have any questions, you could come up to the mic.
Despite all the safeguards, what happens if you can't complete the transfer within 7 seconds, or the 27-second window?
We don't have that option.
Don't have that, so
We don't.
it will just stop?
No, it will not stop. There will be the summit can hold certain amount of data in case the primary or the secondary path are
So you do have a buffer, a cache or
yes,
buffer?
but the goal is to send the data within that
I understand.
window.
But there is a fallback.
Yes. But, yeah.
It's just a follow-up on that. Is that transfer constant, or is that like a scheduled transfer?
Constant.
Constant?
Yes.
My question is towards your failure options during your transfer. I assume it's usually a link that gets congested or the next hop is not reachable. So is your solution there to basically switch paths during the transfer?
Yes, yes. So in a way, we try to automate this switching path
Right.
We don't have an option we have the buffer, but that's not an option. That's like a backup in case there is like a natural disaster, fiber cut, or all the fibers are down. But we try to automate, as I mentioned, from Jacksonville from Santiago to Jacksonville, there is like 25 possible paths that packet can take. So we try to build resiliency based on this partnership with all those
Right.
networks.
So that's the SDN part of your
Yes.
implementation that keeps track of the load or the bandwidth in use on every link, and then says, okay, I've got bandwidth available here, I'm going to switch it on to this path.
Yes, well, there will be a dedicated link for the telescope, and then we have all this resiliency, and then we try to also automate it using SDN.
Sure. Okay. Thank you.
Thank you.
Thank you for the talk. Jelena Mirković, USC. I had a question about your automation and its complexity, and I was curious, how do you test your rules to make sure that you don't have a situation where they are kind of working against each other or taking you into some operational point where you don't want to go?
Well, we test everything. Test and test and test before we put in production, and then we test again. The automation, that's a gradual process. We put SDN in production 2014, and that time we had like no software developers. We had only network engineers. Then we had one software developer. Currently we have a whole team of software developers that develop the software itself. Also we have a quality tester, we have a CDCI, we have all these tools implemented to test the code before it gets to the production.
Okay, so you have some kind of simulation environment that
Testing
replicates your
environment, yes.
network.
Yes.
Yeah, I'm asking because
we do.
As you remember, when Facebook had its downtime, they had a lot of automation, but they had a failure they couldn't predict, and that failure worked against their setup. So.
Yes, I don't want to comment on Facebook, but yes, we do have a testing environment. We have a complete replica of the environment in hardware, and then we test it again.
Yeah, thank you.
Thank you. Any other questions?
Yeah, one last one, if you don't mind. Given that some of these location observatories and telescopes are located in remote locations, how are you able to solve that connectivity? Like, what technology do you use? Extending it to that.
Well, there are a few telescopes around the world that still ship disks. As I mentioned before, there is like there could be one telescope, there could be 1, 2, or in the case of when they created the picture of the black hole, there were like, I don't know, over 7 or 9 telescopes. So they ship the data, they correlate it. Now what we see is that those telescopes are more and more interested in looking to use the research and educational networks to transfer their data, because it's faster, more reliable, and they can complete the task faster.
Yes.
Thank you, VASILKA. So these paths that the data uses, are they layer 2 paths, or do they rely on BGP peering between the different entities?
Well, the network for Vera Rubin is different networks, so that's why we have all these network operators involved in creating the network. We have layer 2, we have layer 3. This one will be layer 2, I think. I can verify that for you.
Anybody else? Well, thank you very much again,
Thank you.
VASILKA. And let's
Okay.
hear it again for VASILKA.
Thank you.